This video is part of an online course of multivariable calculus, and I'm going to talk about Jacobian of a transformation. So let me start. Let's say we have this transformation, u as a function of x and y, and v as a function of x and y. For example, let's say u is equal to x plus 3y and v is equal to 3x squared y. Okay, this is a transformation that transforms x and y into u and v. Okay, we're gonna define the Jacobian of this transformation as this. This is the notation, the partial of u and v with respect to x and y. This is just a notation to saying that I'm taking derivative with respect to x and y and derivative of v with respect to x and y. The Jacobian is determinant of this matrix. Partial derivative of u with respect to x, partial derivative of u with respect to y, partial derivative of v with respect to x, and partial derivative of v with respect to y. Jacobian is very important. Why? It's just because if we have the double integral and inside the double integral we change the variables of x and y into u and v, okay, using this transformation, for example, then du dv, the area element of the transformation in u and v, would be the absolute value of Jacobian. This is basically absolute value of the Jacobian, and then dx dy. Okay, so I can say that the partial derivative of u and v with respect to x and y, the absolute value of the Jacobian, and then dx dy. Why do we use the absolute value in here? It's just because this is the element of the area of or region in UV plane, and this is also the element of the area for or region in xy plane. And since the area is always positive, that's why we use absolute value to get something positive in here. This side is the area positive, this is positive, so I need a positive sign in here. That's why we use absolute value. Just a small note is that we have it also conversely. So conversely, if I have dx dy, it would be, I can define the Jacobian as the partial derivative of x and y with respect to u and v. Okay, and inside the Jacobian I have x with respect to y, x with respect to v, and then y with respect to u, y with respect to v, and then du dv. Okay, so these two Jacobians are inverse of each other. Okay, these two matrices are inverse of each other. So if I have the Jacobian of x and y with respect to u and v, and I multiply by the Jacobian of u and v with respect to x and y, okay, so this one is this matrix. This one is the matrix when I have a partial derivative of x with respect to u, partial derivative of x with respect to y, with respect to v, partial derivative of y with respect to u, partial derivative of y with respect to v. If I do this transformation, I get one. Whichever that is easier you can use. Okay, and very good. So let me give you one example, and the example that I'm gonna tell you right now is polar coordinates, because we use it a lot. So let's see. If we define x to be r cosine theta and y to be r sine theta. Okay, since I have x as a function of r and theta and y as a function of r and theta, I'm gonna use the Jacobian of x and y with respect to the new variables r and theta. Okay, I'm gonna use this one, which is what? The Jacobian is the absolute value of the determinant of this. Actually, let me just explain the Jacobian. The Jacobian is the determinant of this matrix. X with respect to y, x with respect to theta, y with respect to y, or y with respect to theta. So what is partial derivative of x with respect to r? It would be just cosine theta. What is partial derivative of x with respect to theta? It would be negative r sine theta. What is partial derivative of y with respect to r? Would be sine theta. Partial derivative of y with respect to theta, it would be r cosine theta. Okay, now let's see, this determinant is what? I'm gonna multiply like this to find the determinant minus that. So it would be r cosine square of theta, negative and negative positive, r sine square of theta. So I can factor out the r cosine square plus sine square of theta. So this is 1, and so the answer is just r. Okay, that's why I can say that dx dy, okay, dx dy, let me show it to everything. So dx dy would be partial derivative of x and y with respect to u and v, the Jacobian of x and y, which would be just r, and then du dv, dr d theta. Okay, so as you remember, in the polar integrals we use this transformation to write the area, the element area in polar coordinates. So on the next video I'm gonna solve more examples.